Now let's talk about some ranks associated to a matrix. So for an m by n matrix, the row space is the span of the rows. So the row space of A is the span of, and then our notation for the row vectors that appear, that was like, so the first one is 1 comma and then dot running through all columns. And this is all the way down to, there's m rows. And so each of these rows lives in F1n. And the row rank of A is the dimension of the row span. And then we have the same thing all over again for columns. And in a fit of laziness, I'll just do a copy and paste here. So let's see, so the column space is going to be, let's see, denoted colsp of A, and this is going to be the span of the column vectors. So now these are going to be the ones where the first argument can be in any row, and there are, how many columns? There are n of them, and they all live in F1m. And then the column rank of A is going to be the dimension of the column span. Okay, so we can talk about what you can build out of rows, and we can talk about what you can build out of columns. And a theorem, which is hinted at in the book but not actually stated, is that the range of T is isomorphic to the column span of its matrix. I actually talked about this once long ago when we first talked about the rank nullity theorem and the fundamental theorem of linear algebra. Way back in, oh gosh, where was that? Chapter 2 somewhere? So, proof, let's see. Well, maybe I'll just sketch the proof. But the idea is that once you've fixed a basis for V and W, then moving from the transform to the matrix is your isomorphism. So maybe I'll just write that down. So for fixed bases, M is an isomorphism. Okay, and so what does, actually here, let me move that so I can just punctuate my sentence. There we go. And so what that means is that if we look at the range of T, so the range of T, this is the span of TV1 through TVN. right? And this is then going to be isomorphic to the span of M TV1 M TVN. And so what do we have here? This is the span of, and then we've got this theorem that tells us that this is, whoops, the first column of that matrix. And so this is going to be the nth column of that matrix. And I'm basically done now, but just for really hitting it over the head with a hammer, whipping a dead horse, whatever you want to call it. I'll write it back in terms of the A notation, so it looks like that. Okay, and so then this last thing that we have here, this is clearly the column span of A. And so now as a corollary to this, we have the proposition that the book calls 3.117, and that is that if you take the dimension on both sides, then on the left you get the rank of T, and on the right you get the column rank of MT.